Okay, hi everyone. So today we are talk about something a bit more complex, and many people who study coding just hate this part, and it's graph. So first we'll talk about what is graph. So a graph is a nonlinear data structure consisting of vertices and edges. The vertices are sometimes also referred to as nodes, and the edges are lines or arcs that connect any two nodes in the graph. More formally, a graph is composed of a set of vertices and a set of edges. The graph is denoted by GVE. So you can see here is a graph, typical one, and here is a tree, and a tree is also a type of graph because you can look at the definition again. A tree is composed of a lot of nodes, and they are also connected by the edges, and therefore a tree is also a kind of graph. So graph data structures are a powerful tool for representing and analyzing complex relationships between objects or entities. They are particularly useful in fields such as social network analysis, recommendation systems, and computer networks. In the field of sports data science, graph data structures can be used to analyze and understand the dynamics of a team performance and player interactions on the field. So imagine a game of football as a web of connections where players are the nodes and their interactions on the field are the edges. This web of connections is exactly what a graph data structure represents, and it's the key to unlocking insights into team performance and player dynamics in sports. So here we will talk about the components of a graph. So vertices are the fundamental units of the graph. Sometimes vertices are also known as vertex or nodes. Every node can be labeled or unlabeled. So these 1, 2, 3, 4, 5, 6 are nodes. And edges are the lines that connects the nodes. So it can be ordered pair of nodes in a directed graph. Edges can connect any two nodes in any possible way. There are no rules. Sometimes edges are also known as arcs. So edges can be directed or non-directed. So we'll talk about this in the classification of graphs later. So here, type of graphs, and these are two special types of graphs. So first is null graph. A graph is known as a null graph if there are no edges in it. So this is a trivial graph. So they only have a single vertex and they don't have any edges. Here, these are two common classifications of the direction of graphs. So undirected graph is here. So a graph in which edges do not have any direction, that is, the nodes are unordered pairs in the definition of every edge. So when you, for example, traverse the graph, you can go from 1 to 4, and you can also go from 4 to 1. So this is a directed graph. So this is a graph in which edge has direction. That is, the nodes are ordered pairs in definition of every edge. So for example, you can go from 5 to 3. However, you cannot go from 3 to 5 because the direction of the edge, the direction of the line that links these two nodes are in a specific direction. So here, these are connected graph and disconnected graph. So this is the graph in which from one node we can visit any other node in the graph. So this is a connected graph. So it is all the nodes are connected, and when you start from one node, you can visit any other graph, another node in the graph. So this is disconnected graph. So the graph in which at least one node is not reachable from other nodes. So for example, here 5 and 3 are connected, and 1 and 4 are also connected. However, you cannot reach 1, for example, from 3. So you can also see this as two distinct graphs. So here we talk about complete graph. So this is the regular graph that is not complete, a very common one, and here it is complete. So the graph in which from each node there's an edge to reach other node. So for example, 1 here, all the other nodes are connected to it, and 3, 4, for example, the node 3, the 5, 4, and 1 are also all connected to 3. So when the graph is in this way, it is a complete graph. And cycle graphs. So the graph in which the graph is a cycle in itself, the degree of each vertex is 2. So you can see here, when you start from 3, for example, you will visit 5, 4, 1, and you will be able to get back to 3. So it has a cycle inside the graph. And for example, if you want to have an example of a graph that is not that does not contain a cycle, you can just think of a tree, for example. So for example, we have a very simple binary tree here, 1, 2, 3, 4, and this is a tree. It is a graph, and it does not contain any cycle in itself. However, if we add an edge here, so this will not be no longer a tree, and it has been converted from a non-cyclic graph to a cyclic graph. So here we talk about cyclic graphs. So they are a graph containing at least one cycle. So for example, here this graph has only one cycle. It is very similar to this one. And if we add another edge here, it is also a cyclic graph, and it has 3 cycles, this one, and this one. So here, weighted graph. So weighted graph is a graph in which the edges are already specified with a suitable weight, and they can be further classified as directed weighted graphs and undirected weighted graphs. So we will give an example here. For example, this is the city A, and this is city B, and this is city C. So if you are discussing only whether the graphs, you can get from one city to another. For example, here you can get from city A to city B, and you can get from city A to city C, and this is already a graph, and it is not weighted because it only shows whether the nodes are connected. However, we can also add a characteristic to the graph. For example, we know that the distance from city A to city B is 50 kilometers, and we know that the distance between A and C are 100 kilometers. So now we can see that this graph is called weighted because the edges are with suitable weight. They don't have the same distance in this case. And here we are talking about multi-graph. So here is how a multi-graph differs from a simple or regular graph. So in a multi-graph, it contains some parallel edges, but it doesn't contain any self-loop. So for example, a road map is a multi-graph. So you can see from this part that it has 2 edges connecting the node V1 and the node 3, 4. So in a common or regular graph, it only has one edge between the two nodes. However, it has two nodes in this case, and typically when you have multi-graphs, they are usually weighted because if they are not weighted and there are two edges between the same nodes, this is usually useless. So here we have a summary of the common characteristics of a graph. So when we look at a graph, we'll usually think of the characteristics, and first we'll think whether it is connected, then we'll think whether it is directed, then whether it is weighted, is it a multi-graph or is it cyclic. So here we'll just use the example of tree again. So here we come into this graph, and then we'll first think of whether it is connected. So the tree graph is certainly connected because you can get from any node inside the tree from a given node. For example, you can get from here to here, and from here to here, then here, and directed. So in a tree graph, it is directed because the relationship between the father node and the child node is usually directed. So you will get from the father node to the child node. However, it can also be non-directed. So it depends on circumstances. And weighted. So the tree graph is usually not weighted because you just described the in this case it's not weighted because you just described the relationship between the father node and its children nodes or the subtrees, whatever. So we don't give the edges inside the graph a specific weight. And is it a multi-graph? No, because any edge between the two nodes are not repeated. And cyclic, a tree is not a cyclic graph. So because if it is connected, for example, here we add an edge here, it will be cyclic, but it will no longer be a tree. So after knowing the classification of, or you can say the characteristics of common graphs, we'll be talking about the representations of graph. So today we'll just talk about one common way of representing a graph in your coding, in your codes. So the most common way that we use is adjacency matrix. So an adjacency matrix is a way of representing a graph as a matrix of Boolean. So there will be 0 and 1. So let's assume that there are n vertices in the graph. So we'll create a two-dimensional matrix, adjacency matrix n, having dimensions n times n. So if there is an edge from vertex I to j, we'll just mark adjacency matrix ij as 1. And if there is no edge from vertex I to j, we just mark it at 0. So we'll take two different examples of directed graph or undirected graph to show how we use the adjacency matrix to store the graph. So here you can see it is an undirected graph, and it is very simple. It only has 3 nodes, 1, 2, and 0, and it is a complete graph because it has edge from connecting 0 and 1, and also has edges connecting 0 and 2 and 1 and 2. So here you will see that first we are define an adjacency matrix here, starting from 0 to 2. Then we'll look at each node. First is node 0, and we'll then check the relationship between this node and all the other nodes. For example, 0 cannot be connected to itself, so it will be 0 here. Then we'll check the relationship between 0 and 1. So we will see that there is an edge between 0 and 1. So when we want to show this kind of relationship, we will just set adjacency matrix 0, 1, 2, 1. So this Boolean value here stands for that there is an edge between 0 and 1. So adjacency matrix is a directed representation in this way. So it means that you can get from 0 to 1, and since that it is an undirected graph, you can also get from 1 to 0, and this place will also be 1. And that is the same for the edge between 0 and 2 and the edge between 1 and 2. So they will all be 1 in this case, and only the adjacency matrix 1, 1 and the adjacency matrix 2, 2 will be 0 because they cannot be connected to it themselves. So for example, if we delete the node, the edge from connecting 0 and 2 here, so 0, 2 here will be 0 because there is no edge connecting them, and 2, 0 will also be 0. So here it will be very easy to understand how you represent the graph in a adjacency matrix. And it will be pretty the same for directed graphs, because here you have a directed graph, and you have first you have check 0. So 0 does not point to any other node. You cannot get from any other node from 0. It does not point out to any other node. So this whole line will be 0. And we will check 1. Then 1 points to 2 and 0. So you can get from 1 to the node 2 and the node 0. So here inside the adjacency matrix, 1, 0 will be 1 because there is an edge, and 1, 2 will also be 1 and cannot point to itself. So here will be 0. Then you will check node 2. So node 2 only points to node 0. You can only get to node 0 from node 2. So there's only this edge and it is directed. So 2, 0 will be 1, and the other spaces will be put 0. So when you have this adjacency matrix, it will be very easy for you to to understand how many edges it has and how many nodes it has. So that's all for today's activity. Thank you.